In the previous section, we spent quite a bit of time finding limits of various functions, but the only methods that we used there to find the limits were graphing and numerical. That means we either had a graph or we had a table. And by analyzing the graph and the table, we were able to determine the limit of the function at a particular value of x. But having to sketch a function every single time just to get a limit, it can be very tedious, not to mention having to create a table of values every single time that you're given a function and you want to analyze the limit of that function. So what I'm trying to say is that we need to start developing tools for finding limits of functions in a very practical and therefore efficient manner. We already have the limits of two basic functions. If you remember, we already determined what is the limit as x approaches a of a constant function and what is the limit as x approaches a of the function y equals x. So imagine that you have a toolbox and we are going to dump in that toolbox many properties that will allow us to evaluate the limits of functions very easily. And in that toolbox, we already have two such limits. I'm going to put the box right here. I want you to notice that what I'm trying to indicate here is that we already have this tool for evaluating the limit of any constant function. We said in the previous section that the limit as x approaches a of a constant function c is always c. Similarly here, the limit as x approaches a of f of x equals x is always a. So these are two tools that we already have in our wonderful toolbox for evaluating limits. And in this section, if you look at the title right here, we are going to develop many more tools. In fact, we're going to develop about 5 or 6 other tools for finding limits of functions very quickly. And that's definitely a good news, and I'm hoping that you're looking forward to that. Let's get started now building some of those properties so that we can go ahead and start evaluating limits algebraically. As we do that, I want us to make the following or make note of the following conditions on two functions, f and g. So here we have f and we have g. These are two functions. A is any real number. And these are the main assumptions that we're going to make, very important assumptions. We are going to assume that the limit as x approaches a of f exists and is equal to L. We're just going to give it a number, and L is a real number. Similarly here, the limit as x approaches a of g of x exists and is equal to m. And again, I am emphasizing here that L is a real number, and m is also a beautiful real number. Here in this little green part, I am saying, just emphasizing that the limits of f and g must exist at a. This is the main condition for us to be able to develop the following properties. So then, if we make those assumptions, property number 1 says that if we want to take the limit as x approaches a of f of x plus g of x, in fact, I will also combine subtraction if you don't mind. So f of x plus g of x or f of x minus g of x. So essentially, we are creating a new function that consists of the sum or the difference of f and g. How do we take the limit of a sum? How do we take the limit of a difference? Remember that the limits of f and the limit of g exists. If this is the case, then the property says that we can take the limit as x goes to a of the functions individually. So this will be equal to the limit as x goes to a of f of x plus or minus the limit as x approaches a of g of x. And this is nice. Being able to separate the limits is really nice because we know this limit. Remember this limit in the condition above. This limit is equal to L. And we also know this limit. This limit is equal to M. So I can write this as L plus or minus M. So this is what we will be able to do if we ever encounter the limit of the sum of two functions or the difference of two functions. But we need to know the individual limits of f and g. Property number 2. Well, if we have a property for addition and subtraction, why not multiplication? So this property will say that if we take the limit as x goes to a of the product of f of x and g of x, if we do that, then we can take the limit as x goes to a of f of x just by itself and multiply it by the limit as x goes to a of g of x. And this is again possible because we know the limit of f of x and we know the limit of g of x at a. Those limits are going to be L for the first function, M for the other one, so L times M. Property number 3 will say, well, what if we need to take the limit as x approaches a of, let's say, c, a coefficient, times f of x. And this c over here is a numerical coefficient. So this is like having 3 times f of x, or 4 times f of x, or -5 times f of x. So the way that we're going to go ahead and deal with a function that consists of a coefficient times f of x will be as follows. The property says that we can take c because it is just a number and put it in front of the limit. So this will be equal to c times the limit as x approaches a of f of x. I'm going to put brackets over here to keep that limit together with the function. So practically saying, because this is a numerical coefficient, c doesn't depend on x. So it can be taken outside, in other words, in front of the limits, and then the limit will only apply to f of x, because just f of x depends on the variable x. And we know the limit, right? We know that the limit as x goes to a of f of x is equal to L. So this becomes just c times L. We can follow a similar analysis with g of x. Let me do it here on the side. If I consider the limit as x approaches a of c times g of x, the property says that I can take this c right here and put it in front of the limit. So this will be c times the limit as x approaches a of g of x. And this limit right here, we know that this limit is equal to m. So the final answer will be c times m, where m is the value of the limit of g of x. So we have already built three properties right here, three nice properties that will now go nicely into our toolbox and join the two that were already there. So we already have 5 properties at our disposal. We still have a few more, however. So that's going to be property number 4. So far, we haven't tackled division. Maybe it's time to do that. So property number 4 will tell us what to do when we take the limit as x approaches a of f of x over g of x. The property says that because we now have a numerator and a denominator, the limit can apply separately to the numerator and it can apply separately to the denominator. So we take the limit as x approaches a of f of x, all that divided by the limit as x approaches a of g of x. And we know that the limit above exists. The limit above is equal to L, and the limit below is equal to M. Now, for this to make sense, we need to make the following remark that M shouldn't be equal to 0, because then division by 0 is undefined, that limit wouldn't exist. Let's continue now with property number 5. This property will now be dealing with powers and roots. That's very important because functions will have square roots, cube roots. They're going to have rational exponents such as 3 over 2, 5 over 7, and we want to be able to nicely find the limits of those functions. So let's say that we are considering the limit as x approaches a of f of x, this is our function, f of x, raised to the exponent p over q. Here, please keep in mind that this fraction, p over q, is assumed to be in lowest terms. So it has to be completely simplified. Something, for example, like 5 over 7, 3 over 2. All of these fractions are in lowest terms. So if this is the case, then the property will say that if we want to find this limit, we can take the limit and apply it to f of x, to the inside. Notice how f of x is inside of the exponent. So this will be equal to the limit as x approaches a of f of x to the p over q, which in turn, because we know that this limit exists, right, over here above, this limit is equal to L, we can make the substitution, and we can say L to the p over q. Now, I just want to make a remark here. Whenever we're dealing with rational exponents, I mean, if q happens to be 2, imagine that p over q, just imagine for the sake of argument, that p over q is like 3 over 2, L to the 3 over 2. Well then, L to the 3 over 2 really means the square root of L to the third, right, by properties of radicals. That really means that because we end up taking the square root of L, L cannot be negative. So this is a remark that I want to make. I want to say that if, for example, Q is even, if Q happens to be an even number, then the assumption will be that L is greater or equal to 0. L has to be positive. Otherwise, this number will not exist. But I think that that makes perfect sense. Similarly, I can have a negative fraction, right? Nobody says that that p over q has to be positive. For example, again, imagine that we had L to the negative 3 over 2. So then that means 1 over L to the 3 over 2, which means 1 over the square root of L to the third. Well, the point is that now L goes down to the denominator. So in this case, L cannot be 0. So I'm going to make that remark as well, that if P over Q is less than 0, then L cannot be equal to 0, because then I will be dividing by 0, and again, that is undefined. Let's continue discussing powers. We're going to now consider a number n, and n is a positive integer. So let's say it's a natural number. A natural number. If you remember, the natural numbers are the counting numbers, 1, 2, 3, 4, 5, and so on. My goodness, we have so many functions that involve powers of n, like x squared, x to the third, in situations like that. So we want to be able to find the limits of functions like that in an easy way. So how do we do something like this? Let's say that, again, we consider the limit as x approaches a. Why don't we use g of x this time? We have been using f of x quite a bit. So let's say g of x to the exponent n. This is very similar to the limit that we tackled above with a rational exponent, p over q. The property will say that the limit is going to apply to the function inside, to g of x. So this is going to be equal to, imagine this over here, the limit as x approaches a of g of x. And we know this limit. We know that the limit of g at a happens to be equal to m. So this will be equal to m to the n. That's how easy it is to handle powers that are natural numbers as well. And what happens if we consider the limit as x approaches a of g of x to the 1 over n? In fact, it kind of seems silly to tackle this case over here since we already did it here for a more general rational exponent, p over q, but I'm going to go ahead and do just 1 over n as well. Well, if we do that, I'm going to do it because of radicals. This is the same thing as having the nth root of g of x. And according to this property, if we have the nth root of a function, the limit can apply to the function that is inside of the radical. So this will be equal to the nth root of the limit as x approaches a of g of x. And we know that the inner limit exists. That limit is equal to m. So then the final value of the limit will be the nth root of m. And just again, making an obvious remark, I hope, that if n happens to be even, it is important for m not to be negative. So I'm going to make that remark right here, that if n is even, then we know that m has to be greater or equal to 0. I want to go here and make a few additional remarks. I want to expand on property number 1. If you remember, property number 1 said that if I take the limit as x approaches a of the sum of two functions, I am going to ignore subtraction. I'm going to focus on addition here. The property told us that this would be equal to the limit as x approaches a of f of x plus the limit as x approaches a of g of x. And we can do that, we can separate the limits of these functions because the individual limits exist. If you remember there, we were using L and M for the values of those limits. The extension to this property that I want to make is to note that this property applies to the sum of more than two functions if necessary. We are not limited to just two functions. For example, if I consider the limit as x approaches a of f of x plus g of x plus h of x, let's do one more, plus k of x. Then the property says, well, not a problem. It says as long as each individual function has a limit at a, then we can separate, we can apply the limit to each function at a time. So we can say that this is equal to the limit as x approaches a of f of x plus the limit as x approaches a of g of x plus the limit as x approaches a of h of x and plus the limit as x approaches a of k of x. And then because these individual limits exist, then you're going to get a real number for this limit, another real number, another real number, and another real number. And you'll be able to add those numbers and get one single real number as the value of the entire limit. Another remark that I want to make here is the following. We already know that the limit as x approaches a of a constant function is always equal to c. And we also know that the limit as x approaches a of the function f of x equals x is equal to a. And these are limits that I told you since last section we can now assume that is always true. So what happens now that we have the new properties of limits that we just discussed a few minutes ago? What happens if all of a sudden we want to find the limit of power functions? Here I am assuming that I am working with the function f of x equals x. And let's say that that I have a question that is asking me to state or to find the limit as x approaches a of x to the n. N can be, n again here is a natural number, the counting numbers, 1, 2, 3, 4, 5. How do I find this limit? So I know that I have now properties of limits. One of the properties of limits, I think it was the last one, said that I can take the limit and directly apply it to x. I am thinking of x as the inside function. I can do that, and I can leave the exponent outside. And what is nice about this is that I know this limit, right? This limit is right here. The limit as x goes to a of x happens to be equal to a. So then I end up getting a to the n as an answer. And this is another kind of fact that we are now going to have. We're going to add this to our toolbox as well. So from now on, what I'm trying to say that from now on, whenever you encounter the following limit, the limit as x approaches a of x to the n, you can always substitute a into the variable and right away say that the value of the limit is a to the n. I'm going to also circle this in blue, okay? Similarly, nobody says that the exponent has to be a natural number. What if the exponent is a rational number? Something in the form p over q. If this is the case, then if I have to find that limit, again, I think that the last property said that I can bring the limit and apply it to the inner function. So this will be equal to the limit as x approaches a of x, and then the exponent is kept outside. That is going to be equal to, remember that this limit is equal to a. So then that's going to be equal to a to the p over q. So then from now on, this also goes in our toolbox. The limit as x approaches a of x to the p over q is equal to a to the p over q. Always, always, always. So these are things that we're going to assume. And another remark that I want to make is that the properties that we just developed also work for one-sided limits. Let me even write that down because I really would like for you not to forget that. So all properties P1, P2, P3, P4, and P5, all of these properties also apply when working with one-sided limits, with one-sided limits. The same conditions, the same conclusions apply. In one of the examples that we're going to tackle later, you're going to see that I will apply the same properties even though it is a question about one-sided limits. So here is our toolbox once again, and I want to start putting things in there. We already started, but let me go ahead and somehow make it obvious here. We already have these two tools from section 2.2, and now we know that we can dump in here the 5 properties that we just discussed. I'm going to call them P1, P2, P3, P4, and P5. These are tools that we have to evaluate limits. And other tools that we have are the one that we just discussed a few seconds ago. We now know that the limit as x approaches a of x to the n is equal to a to the n. We know that. And another tool that is going to go in here is the limit as x approaches a of x to the p over q is equal to a to the p over q. My goodness, if you think about it, our toolbox is already getting very, very rich.